To introduce Anand here, who's going to give the final talk of this conference. So Anand got his PhD from MIT. He was in the physics department, supervised by Aram Arrow. Then he went to do his postdoc in Cornell. Anand's work is really incredible. It lies kind of in the intersection between quantum mechanics and mathematics, in particular on kind of quantum complexity. And his work, in particular on proofs with entanglement, has been really groundbreaking. He won for that Best Paper Award in FACS 2019, I believe. But really, his work is beautiful and fundamental. And so without further ado, it's a real pleasure. Oh, wait, before that, the most important part, that next year we were extremely fortunate to have Anand join us at MIT. So he's going to be a tenure track faculty at MIT starting next year. Anand, we're super excited to have you in the neighborhood. And without further ado, Anand, you're on.
Okay, well, thanks for the very kind introduction. So this is joint work with a bunch of people. So I had them all on this first slide here. So it's Zhengfeng Ji, Thomas Biddick, John Wright, and Henry Yuan. I guess I'll just get right into it. So this talk is about interactive proofs in the setting of quantum. And I realized, when I wrote this talk, I wasn't quite sure what this audience would be like, but I realize now that people here know interactive proofs fairly well. So can maybe go a little bit faster at the beginning and get to the exciting parts. Okay, but just to set the context a little bit, we all have heard of quantum computers, and we know that quantum computers seem to have sort of new powers that you don't have with classical computers. And the famous things you hear about are all sort of maybe more quantitative things, like you can efficiently do certain things that you can't do otherwise. With a classical computer, like factor a large number or simulate a chemical reaction or so on. But there's also sort of qualitatively new things that you can do with a quantum computer, and that maybe is closer to the theme of this conference. So there's things like you can generate true randomness using quantum mechanics, which is something that doesn't really make sense in the classical world. And you can do things like key exchange and so on. So there's a lot of potential here for exciting things to happen. And quantum computers, I just want to plug that they are not entirely theoretical. I mean, people are working on building them, and there's been progress, and there's devices with lots of qubits now that can do interesting things. So it's really an exciting time to think about these things. And I guess what this talk will be about is sort of an instance where quantum computation sort of yields a kind of qualitatively different behavior in complexity theory, which I think is kind of different from maybe the examples that you normally see. So okay, so to jump right to the results, so if you want to fall asleep after this slide, that's fine. So this talk is, I'm really a complexity theorist, so this will be really about, sort of from a complexity theoretic viewpoint. And the main question that we study in this work is, what's the power of, what power does quantumness give you in the setting of interactive proofs from a complexity point of view? And to be really specific, the class that we study is something called MIP star. So what's MIP star? Well, I'll give you a more formal definition later on, but basically it's the class MIP of multi-prover interactive proofs, which you've seen in previous talks in this session, plus quantum entanglement, which is sort of uniquely new resource that you get in quantum mechanics. And so what do we show? Well, just to set the landscape here, if you remember your complexity theory, we have a characterization of classical MIP. We know exactly what it's equal to. It's equal to NEEXP. And more importantly, so these classes like P, NP, MIP, and NX, they're all computable. So they're classes of computable problems. Now, on this diagram, I've also drawn sort of on the right over here an uncomputable class. So this is the class RE. It's the class for which the halting problem is the complete problem. And so, there's no algorithm that can solve all problems in RE. And then, okay, what do we show? Well, okay, it was in the title. Basically, the main result is that MIP star, so you take this classical class that was nice and well-behaved, and you add a quantum to it, it suddenly jumps up in power to being equal to RE. So in particular, it's no longer computable, contains uncomputable problems. Okay, so that's, I think, from a complexity point of view, that's really neat that you have this kind of surprising difference. And also, it turns out that there were, consequences from this sort of beyond what you'd expect. So showing this equality here also leads to the resolution of some problems in like the foundations of quantum information and pure math. So just as a preview of the talk, I'll start by, so for most of the talk, I'll tell you about the complexity theory of this. I'll sort of define, MIP star and explain why, what the challenges are, trying to understand it. And then I'll tell you how our proof goes to show this result. And then at the end, I'll say just a little bit about these connections to physics and math. Okay, so I guess I'll jump right into it. So, okay, so these slides maybe can go by a little bit faster than I was expecting. So, okay, so this is just, I want to review what like the notion of an interactive proof is. I'm sure you all are quite familiar with this, but just to set some language, I guess we have a prover. This is just the basic setup. You have a prover that's all powerful, but untrustworthy. So, you're making no like cryptographic assumptions of any kind on the prover. They can do literally anything they want. You have a verifier that is computationally bounded. So the verifier we'll always think of as being a classical polynomial time machine. And then, the prover is supposed to try to certify to the verifier, the answer to some decision problem. So what that means is, well, you can just think about the basic example of NP, like if you have an NP proof system for something like 3 colorability of a graph, it means you have sort of 2 properties. You have completeness, which means that, if you're given an instance of the problem, like you're given a graph and you want to know whether it's 3 colorable, if that graph is 3 colorable, then there should be some way for the prover to convince the verifier of that fact. And indeed, in this simple proof system, the prover can just write down the coloring and send it to the verifier. So that's, this completeness property. On the other hand, you have to have soundness. So soundness says that, if the answer was no, so say you start with a graph that's not 3 colorable, then there's no way for the prover to fool the verifier. So there's no coloring, in this case that the prover can write down that the verifier, cannot detect is wrong. It's like in this instance, the verifier just does the very simple algorithm of, it just checks, every edge, whether the color constraints are correct. And it can see that, for any coloring that the prover claims, it'll inevitably be wrong. So that's the basic setup when you have an interactive proof. Actually, this is not even an interactive proof. This is just like, a proof system, but you can add interaction. So, the basic class here is something called IP. And it's when you have a prover and a verifier as before, but they're allowed to exchange, multiple rounds of messages. And in particular, the verifier gets to generate random challenges to send to the prover. And this is already, we know that this is equal to P space. So this is more powerful than NP, we think. And it's really because, this interaction with the prover, it really helps, I guess, in this sort of soundness property. Like it makes it much easier for the verifier to detect when the prover is telling a lie. So that's sort of what makes the class as a whole more powerful. And you can think about that as like, I don't know, like an oral exam of the prover. You can cross-examine it and detect inconsistencies. So that's IP. And what about MIP? Well, it's sort of the same model, but you have more than one prover. And for that to make sense, you have to make some sort of assumption about the provers. And the assumption that we make is sort of the following, that these 2 provers, I've called them Alice and Bob here, they can coordinate to whatever extent they want in advance. So they can meet up beforehand. They already know the instances. They know like what SAT formula or graph you're talking about, and they can prepare a strategy for that instance. They can write down some deterministic bits. They can even flip some random coins and like record the results of those coin flips and store all this stuff in however much memory they want. But then they go off and get separated. So once the protocol starts, these 2 provers are physically separated or somehow prevented from communicating with each other. So there's like this wall between them. And then the verifier gets to generate its random challenges for each prover and to wait for responses from them and decide whether to accept or reject based on these responses. So really the key difference here between MIP and IP is this non-communication assumption, right? The fact that how much coordination they do in advance, once Alice gets her random question from the verifier, she has to answer without knowing what the random question that Bob received was, and vice versa. And so this power, this really gives a lot of power to the verifier in this setting, because the verifier knows what's going on, but the provers don't. And so as a result, this class you can show is even more powerful than IP. And so you get this result that MIP is equal to NX. So there's like a protocol in the setting where a polynomial time verifier can be convinced that an exponentially large graph is 3-colorable. And really just to emphasize this again, like where is this power coming from? It's all coming from this non-communication assumption that lets the verifier do these sort of very strong tests on the provers. Okay, so that's MIP. And okay, I had included a slide trying to justify why one would want to study this, but I think that would be preaching to the converted here. So I'll just say that MIP has had a ton of applications to a lot of things, including like pure complexity theory, like the PCP theorem and so on, and also like many interesting protocols for other things, like things like zero knowledge proofs and cryptographic sort of ideas. So it's a cool class. It's been a very fruitful object of study. Now this talk is not about MIP. It's about this version of MIP with quantum entanglement, right? So this thing called MIP star. So now I'm going to define what the setup is there. So MIP star is sort of like almost like, I don't know, I think one of the most natural ways you could take MIP and generalize it into a quantum world. So the way it's defined is, I guess you had a couple of choices in how you define it. And the way it works is we're going to keep the verifier as limited as possible. Generally the spirit of interactive proofs is that you want the verifier to be not very powerful. So we'll keep the verifier as being a classical polytime machine. We'll just let the provers have quantum power. And this sort of makes sense because already in MIP, you assume that the provers are computationally all powerful, that they can do whatever computation they want. So we're just now adding sort of like some sort of physical power to them. You're saying they can do whatever computation they want, and they're allowed to manipulate quantum states. And then how does this all work out with this non-communication assumption? Well, here's how you can define it. Well, you can say that in this coordination phase, before the provers are separated, when they're preparing their strategy, in addition to writing down whatever classical bits they want on whatever tape, they can also prepare any quantum system they want. And you can just think about that in terms of qubits if you'd like. They can prepare any number of qubits that they'd like in whatever state they want, and then split them up amongst themselves. Alice will get some share of the qubits, and Bob will get some share of the qubits, and these things maybe have been placed in some special state in advance. And then, once you run the protocol, you can, when you go into this like non-communicating phase, when the interaction happens, each prover will be allowed to do local operations on their side of the qubits. And really what that boils down to is, they can apply any quantum measurement they want to their qubits. And they can use the outcomes of those measurements when they're trying to come up with answers to the verifier's challenges. So that's the main difference from MIP. And you might ask, well, okay, does this non-communication assumption even make sense in quantum mechanics? Well, the answer is yes. I mean, I guess we heard a lot about this from Claude in the last session. There's ways you can sort of enforce this if you use like relativity and the speed of light barrier. So that's why there's a picture of Einstein here. So this is really kind of meant to be as analogous to MIP as possible. Just you're giving the provers this little extra power of preparing a quantum state. And so now the whole question we're going to ask is, well, how is this class different from MIP? And really, what does this shared quantum state do to the class, compared to shared random bits, which is what you had in the classical setting? Okay, so in order to explain sort of why you might even expect things to behave differently with quantum, I'll just have to give you a super quick crash course in quantum. So this is maybe stuff that you've sort of seen, and I definitely won't go into any of the math, but just so for an intuition, quantum mechanics is sort of like a generalization of probability theory. It's like a generalization that works with sort of complex valued vectors. And you can think about it, just like in probability theory, you have probability distributions. In quantum mechanics, you have states. So a qubit or a set of qubits can be in a state. And so a state of a qubit could be something like 0 or 1. So these are, you can think of them as like classical states, or it can be any sort of superposition of those. And that's supposed to be kind of like the analog to, like a probability of being some chance of being 0 and some chance of being 1. And then how do you convert these things to probabilities? Well, that's the operation called measurement. So if you take a qubit and you apply a certain measurement to it, you get an outcome that's classical, but that outcome is inherently random. There's no way to predict that outcome in advance. And sort of exactly what outcome you'll get, it depends on what state the qubits are in and also what measurement you do. And so, there's a lot of possible states that you could prepare, and you'll get like, different measurement outcome depending on which state you prepare and what measurement you apply. So that's the basic setup you have when you say like 1 qubit. Now, in this talk, the phenomenon that really will be important to us is something called entanglement. And that's something that shows up when you have more than 1 qubit or more than 1 quantum system. So what's entanglement? Well, it's kind of like in this generalization of probability theory, it's the thing that corresponds to correlation, sort of. So you have 2 qubits, they could both be in like a joint state that's sort of a classical joint state. Like it could be qubit 1 is 0 and qubit 2 is also 0, or maybe 0, 1 or 1, 0 or something like that. But you could also have these sort of correlated, quote unquote, states. And these things are called entangled. So they could be sort of, there's some weight on the 0, 0 outcome, and there's some weight on the 1, 1 outcome. So in particular, one state that we'll see a lot is this thing called the EPR pair, which is sort of an equal superposition of the 0, 0 and the 1, 1 states. So, just like with a single qubit state, like these 2 qubit states, you can convert them to probabilities by measuring them, right? If you measure them, you'll get random bits out. And if you measure these 2 entangled qubits, in a state that's entangled, you'll get correlated random outcomes. So that's sort of the connection to correlation here. And so the real question you might ask is, well, that's great. When you measure them, you get correlated random bits out. But so does that mean that you can model all of this just with like, I don't know, correlated coins or something, like just some classical model underneath? So how is this really different from classical probability theory? So that's Anand, a question. Yeah.
Oh, sorry, 1 second. There was a question, but I think it's relevant at this point, which was asked whether the Alice and Bob have entangled states. So that's very important, right? So maybe you can emphasize the entanglement of that these quantum states are entangled.
Yes, very good. Yeah, so okay. So yeah, Alice and Bob can share entanglement. Yeah, so they're allowed to prepare, any state they want in advance. And then, yeah, in particular, they could prepare an entangled state and then split it up. Okay, thanks. Okay, so I guess what I was going to say is that, indeed, entanglement is different from classical correlation. And actually, this is sort of historically very interesting. This was discovered sort of in the foundational physics community by Bell in the 1960s. And really, the argument he came up with to show that these things are qualitatively different is an interactive proof. Like, he didn't use the language interactive proofs because it didn't exist at the time, but that's exactly what he came up with. So he gave an example of sort of a toy interactive proof in this multi-prover setting where entanglement lets the provers do something that they could not do with any amount of classical shared randomness. So just to make this really concrete, I want to show you the example, and maybe you might have seen this. It's this thing called the CHSH game. And so it's the same setting that you had in MIP or MIP star. You have these 2 provers, they get a random challenge from the verifier and they respond with an answer. It's sort of the simplest possible setting you could have, in that the random challenge for each prover is just a single bit. So, the verifier sends either a 0 or a 1 to each prover. And they're sampled, the way the verifier generates these things is it just samples them uniformly, at random from all possible pairs of bits. So, Alice gets a 0 or 1, and independently Bob gets a uniformly random 0 or 1. And then what's going to happen is that, the provers are supposed to come up with an answer for the verifier, and then the verifier will decide whether to accept or reject based on this weird rule here that I've written in this table. And sort of the rule is going to be the following. So, there's 4 possible pairs of questions that the verifier could ask the provers. And in 3 of the 4 cases, the verifier is going to say that, to accept the prover's answers if they are equal. So, if the questions were 0, 0 or 0, 1 or 1, 0, then the verifier will accept if Alice and Bob give the same answer. But if the questions were 1, 1, so in this 4th case, the verifier will accept only if Alice and Bob give non-equal answers. So if you think about this, and think about any classical strategy using any amount of shared randomness that you prepare in advance. Well, first of all, you can, by a convexity argument, see that shared randomness doesn't even help you. So actually, a deterministic strategy is as good as any other strategy. And really, there's no way to win this game with certainty, because if you're Alice and you get the question 1, you have no way of knowing whether you're in the case where you should be giving the same answer as Bob or the case where you should be giving the opposite answer as Bob. And indeed, the best thing you can do is just to win 3 out of these 4 cases. So the best probability of success for any classical strategy is just 3/4. And then what Bell showed is that if Alice and Bob are instead quantum and they share an entangled state and they apply certain measurements, like a very specific collection of measurements, then there's actually a way for them to win this game with a probability that's strictly greater than 3/4. So you can actually get up to something like 85%. This is like a half plus √2/4, if you wonder where the magic number is coming from. So that's really sort of like an operational proof that entanglement is like different from classical correlations. It can let you do something that you couldn't do, in the classical setting. So, okay, so this is, I think, really the example that shows you that something interesting might be going on with MIP star, right? There's this, somehow you gave these provers that were already, all powerful. You just gave them this physical ability, and now they can do more things. So that hopefully, is like the first motivation for why this class might be interesting. Well, there's this like weird surprise that you get in this toy example. So maybe, when you look at more complicated examples, you can get some even more interesting behavior. There's also 2 more points that I think are really nice about the CHSH example. One of them is that if you think about the setup, really, the classical, the verifier here, the only like party that you need to trust is purely classical. But it's actually learning something about these provers that are quantum. And so this is actually maybe sort of a setting that you might think is kind of realistic in the real world, and that when we work with, say, a quantum cryptographic protocol, we as the users are classical beings, but these things are being implemented by some quantum devices that maybe we don't have a good way of looking inside and seeing whether they're working correctly and so on. And so all we get is like, some classical measurement outcomes that come out of the devices, right? And so one message of the CHSH game is that you can actually learn something just from these classical outcomes. You can say something like, this is proof that these devices are doing something quantum, right? And the way that you'd said in the CHSH game is that if you play this game and you observe that the provers are winning with a probability greater than 3/4, right? That's a certification that they're doing something that's not classical, right? So that's certifying just through these classical measurement outcomes that something non-classical is going on. So that's an idea that's showed up a lot in quantum crypto. It's something that's called device-independent security, and people have device-independent protocols for tons of things now. And just another way of sort of rephrasing that is that this is really kind of like a different kind of interactive proof. It's like an interactive proof for a physical property. And indeed, it's the physical property of having an entangled quantum state, right? And so we know about interactive proofs for computational problems, but this is something kind of qualitatively different. So those are, I guess, the main points I want to say about the CHSH games. These are, the reasons I think that MIP star is sort of qualitatively very interesting. Okay. So hopefully I've convinced you of that. And now we can move on to how you would actually show a computational bound on the power of this class. Okay, so there's, whenever you have a complexity class, you want to understand it, there's 2 questions you could ask, right? You could ask, can I show an upper bound on how powerful it is? I can say it's at most as powerful as some other class, or can I show a lower bound on it? And for MIP star, it turns out that both directions are kind of tricky. So let me start with the upper bound. So for the upper bound, the main challenge here is if you want to show an upper bound for MIP star, you sort of ultimately need to understand what kinds of quantum states would the provers possibly need, right? Like, is there, one approach to showing this upper bound would be, well, if there's some, if I know in advance that say, two provers that participate in a polynomial size interaction never need more than a polynomial number of qubits to achieve whatever, maximum success probably they could achieve, then I'd have an upper bound in this class because I could just do sort of a brute force search over all strategies that use the polynomial number of qubits, right? Unfortunately, we do not know of any such nice bound. So we have no idea, whether in general to achieve something like the CHSH advantage, you might need, an enormous number of qubits. So I guess actually, like one conclusion of this work is that indeed there are examples where you need, like uncomputably large numbers of qubits to achieve a quantum advantage. But just, to explain why that affects or how that goes into the upper bound, sort of, if you want to get an upper bound on MIP, I guess this is sort of something I maybe already implied, but if you want to get an upper bound on MIP, what's one way you could do that is you could just do sort of a search over all the strategies that the classical provers could use, right? And in MIP, you can sort of restrict yourself to deterministic strategies, and then these strategies are just, you can describe them as big lookup tables, right? Like for every question that the prover asks, the verifier asks, the prover has to have a response written down somewhere. And you can search over all of these, strategies in non-deterministic exponential time. So that's where this upper bound of MIP being contained in NX comes from. And if you try to apply the same reasoning to MIP star, sort of the best you can do is just write down the following algorithm, which is you just search over all prover strategies using an increasing number of qubits. So all the strategies that are classical, and then all the strategies using 1 qubit, and all the strategies using 2 qubits, and so on. But you don't know when to stop looking for strategies because you have no bound on how many qubits the provers might need. And indeed, we have like these, it's not just in general, we don't know, but like, there are specific examples of games that are very small, and like, they look just like the CHSH game with a little twist. And for this particular game, like, we don't actually know how many qubits you need to achieve the optimum. It's conjectured that you might actually need an infinite number of qubits. So that's sort of the main challenge in showing an upper bound. And since this enumeration doesn't stop, the best trivial upper bound you get is MIP star contained in RE. And actually, since I'm going to show that this upper bound is tight, I'll actually not be able to improve on any of this, right? So in general, there is no good upper bound on how much entanglement provers might need to play one of these, to succeed in one of these protocols. So that's the difficulty with the upper bound. Now you might say, okay, let's switch to the lower bound. To show that MIP star is at least as powerful as some other class. And in particular, you might think, well, MIP star was just, MIP, but with some extra bells and whistles added. It should be at least as powerful as its classical counterpart, right? Like that seems like it shouldn't be hard to show. But actually, it turns out that that direction is also quite tricky. And here's the reason why. Well, it's the fact that in MIP star, you're giving extra power to the provers in a proof system. And as we saw, at the very beginning, there's always these two considerations in these proof systems, right? The completeness and the soundness. There's this case where the provers are honest and trying to prove a correct statement, and when they're dishonest and trying to falsely prove a false statement. So giving the provers more power could make the dishonest provers more powerful as well, and that would reduce the power of the complexity class as a whole. So it's conceivable that MIP star could have been less powerful than MIP. And indeed, like examples are known of particular protocols that are sound classically, but not sound against entanglement. So this is like a real possibility.
Anand, can I stop you for a second? There's actually a
Sure.
question that I think would be good to plug through. So the question is, does infinite number of qubits also mean infinite running time for provers? And in particular, I think we should emphasize exactly what that there's no time bound or anything on the honest or malicious provers.
Good. Yes, that's right. Yeah. So there's no time bound on the provers, and so indeed, if the provers had to implement something on an infinite number of qubits, that would that would take, an unbounded amount of time. But you're not making any assumptions on their computational power.
Great, thanks.
Sure. Okay, so okay, I guess the point I wanted to make here was just, it was conceivable that MIP star would be less powerful than MIP because of this extra power for the dishonest provers. And actually you can show that that's not the case, but that requires, taking a particular MIP protocol for NX, for an NX complete problem and going through all the steps and really showing that, entanglement doesn't let you cheat any of the steps. So that was done by Ito and Vidic, and it was like, technically pretty challenging work. So, somehow, to go beyond, to improve this lower bound, which is what I'm going to have to do for you, you have to go beyond sort of the classical result, which is NX. And as we saw in the previous slide, that NX upper bound on MIP sort of came from the fact that you could enumerate over these strategies. So you need to somehow design a protocol where the provers use so much entanglement that you can't enumerate over all possible strategies within NX. So there has to be some strategy where the provers use a lot of entanglement, but you also need the verifier to be able to certify that the provers are not using that entanglement to do something to cheat somehow. So you need to somehow design a protocol where a classical verifier can somehow force these quantum provers to prepare very large quantum states and also execute very well-controlled operations on them. And that's really what we're gonna show. So the basic approach here is, there's sort of like, I feel like two parts to this. Is the first step is just, this idea of how do you get a verifier to force the provers to use a lot of entanglement in a specific way. I'll talk a little bit about that. And then I'll show you, once you sort of have that, how you can design protocols for computational problems and ultimately for the halting problem, which is the complete problem for RE. Okay, so for the first part, just this question of how can a verifier, force provers to use, a big entangled state in some way. I really have to go back to the CHSH game I showed you before and tell you one more really nice property of it. So I said earlier that the CHSH game is like kind of an interactive proof of entanglement, right? If you run it and you observe that the provers succeed with high probability, then that implies that they have some kind of quantum entanglement that they're exploiting. But actually, it's a lot stronger than that. So it turns out that CHSH has this property that it's called rigidity, or some communities call it self-testing. And what it shows is that not only can you use it as an interactive proof of entanglement, you can use it as a proof of a particular specific quantum state. And the way that works is that you can show that any pair of provers that succeeds in the CHSH game with a probability that's close to the optimum. So this optimum was this 85% that I wrote down earlier. Anything that's even close to 85% has to come from using a particular quantum state, this EPR state. So if I'm this close to the optimal win probability, then I can get a bound on how close the prover's shared state is to this EPR state in some appropriate distance metric, which is a little bit tricky to define, but there's a reasonable one that you can define. And so the way you can think about this is that this is really a way that the verifier can gain control over the provers. Actually, there's this great phrase that showed up in a paper title by Reichart, Unger, and Bazzarani that says, this is like a classical leash for a quantum system. That if the verifier plays this game with two provers and it just observes their win probability over many rounds of CHSH, that's enough to certify that the provers are exactly using this particular quantum state. And moreover, I didn't write it here, but it's not just the state that you certify, it's also the measurements that you apply. So there's not only a unique quantum state, but a unique set of measurements that work to achieve this. So really the CHSH game can be used to certify the complete behavior of these quantum provers. So that's like an extremely strong property, and our main goal in this part will just be to scale up this idea to give you a family of games or protocols that can do the same sort of thing, but for much larger quantum states. And in particular, we'll look at the state that's just many copies of this EPR state here. And ultimately, the goal will also be to do this sort of as efficiently as possible, to have the verifier do as little work as possible to verify these large quantum states. So there are a couple ideas that go into this. I can't really show you the details of the protocols, but I'll just say, sort of the first thing you might try is to parallel repeat this CHSH game. Just run it many times in parallel, and hopefully that can certify many copies of this EPR state. And indeed, you can sort of do an analysis like this. So something we did in joint work with Matt Kudron, not for CHSH, but a different game called Magic Square, but that's closely related. And you can get some guarantees, but they sort of have kind of an annoying property that they only kick in when you have provers that are sort of, so close to they're like inverse polynomially close to the maximum winning probability. So the amount of accuracy you need to know the prover success probability to is a function that sort of shrinks with this parameter n that tells you how many copies of the EPR state you're trying to test. And that's sort of not very nice when you're trying to use this as, as a subroutine in other protocols. And really what's going on here is this sort of fact about quantum states that they just don't, it's sort of generally a bad idea to think of a quantum state as sort of something you can access one qubit at a time. Like if you have a many qubit quantum state, you have to sort of look at the whole thing all at once. And this is a nice quote by John Preskill that he uses in a lot of his talks that like, like in a quantum book, sort of like all the information is like in between the pages. If you read it one page at a time, you won't get anything out. So that's just sort of like an intuition, but hopefully it can motivate what's coming next. So really the way we were able to go beyond this is to use some ideas that came from classical complexity theory, and in particular the PCP theorem, or sort of like related ideas in error correcting codes. And so it's this concept of what's called local testability. So in the PCP world, I guess the way this idea shows up is that it's often the case that you have some large object that's supposed to have some sort of global structure to it. You can detect that structure by just probing the object in a few random points. And so like a canonical example of this is if your object is just a Boolean function over the Boolean hypercube. One thing you can do is you can detect whether that function is close to being a linear function by just probing it at sort of 3 random points. So this is this linearity test of Blum, Luby, and Rubenfeld. And so you just check that, you just like pick 2 points and you look at the line through them and you check that the function obeys the linearity property on this random line. And if that's true, then it has to be close to being linear. So really, what we're trying to do in the quantum case is kind of a generalization of this idea of local testability, but for quantum states. So we want to design some sort of test where the verifier can just, ask the provers to do a few measurements on their quantum states. Can send like a small question to the provers, get back a small answer that contains the results of a few measurements, and use them to detect a global structure in this big quantum state that the provers are supposed to hold. And so sort of like, similar to this PCP sort of setting, but a little bit more challenging in that, you have this idea that the verifier is classical, but the provers are holding a quantum state, but you only have access to that quantum state through the untrusted measurements the provers make for you. So it really seems like, there's not a lot of that the verifier has to hold on to. But nevertheless, I guess the main point I can make is that it turns out that it is possible to generalize these local testability ideas, even to this quantum setting, sort of by, using sort of the ideas that went into the CHSH game as well. And you can actually come up with like very precise sort of generalizations of these classical tests for say, Boolean functions and so on. So one thing you can do is you can take this BLR test for linear functions and in a certain way you can merge it with the CHSH game, and you can construct a protocol where a verifier can test that the provers have n copies of the EPR state, doing only, polynomial and n work. And that's already, very useful for things, but it turns out you can sort of improve that even further by, if you use like, a fancier test than this BLR test for linear functions, if there's these like fancier tests for low degree polynomials, if you use those as, your building blocks for your protocol, you can design a protocol where a classical verifier can actually test that quantum provers have 2 to the n EPR states, where the verifier still only has to do polynomial amounts of work. So these are both joint works with Thomas Wittig, and I won't show you how the actual protocols work, but I'll just say this protocol here, the one that certifies 2 to the n copies of the EPR state, that'll be the main tool, one of the main tools I'll use in the next part, where I show you the actual protocol for the halting problem. So before I go on, I'll just say that the main thing to take away from here is that the verifier in this protocol is only doing polynomial amounts of work, and yet it can certify this exponentially large quantum object that the provers hold. And this sort of quantitative relationship between polynomial and exponential, that's going to be important in what follows. Okay, so that's all I wanted to say about how you design these protocols for testing quantum states. And maybe the main takeaway actually from that is, if you're not a quantum expert, is just that these sorts of very strong testing protocols are possible in the quantum world, that you can actually certify quantum states with only classical communication. So I think that's just a cool phenomenon to know about.
So Anand, maybe since we're going to part 2, I'll take some time for a quick question. So Adam, you had a great question. Maybe you want to unmute yourself and ask it?
Sure. So my question was, how does the power of the model change if you want soundness against non-signaling provers, but you still want you still want completeness for like achievability by the honest provers using quantum systems?
I would think in that case that you're not going to have, I would think you would just be in X at that point. Okay, I'm not a non-signaling expert, but I think, I mean, so if you have, because non-signaling provers, like the set of things they can do is characterized by some convex polytope that you can sort of check membership in exponential time. And I think in the honest case, the provers could just be classical and things would.
Yeah, I think my guess is probably even if you allow the honest provers to be non-signaling, which is more than quantum, it's still an X. But I need to recall the details, but that's my guess. Okay, I don't see any other questions, but if anyone else has a question, just raise your hand. I mean, virtually raise your hand. Let me, meanwhile, maybe ask a quick question. So you said you can test for EPR pairs, but I don't quite understand what that means. Because, for example, suppose you and I are provers and we have almost an EPR pair, like 0.499999, it's 00, and will the verifier be able to catch that?
Yes. Okay. Let me just go back to the CHSH slide. So really, what I guess the question is really all about what this distance metric is here that I have, right? So
I see. I missed that. Okay, you're saying that we're close to an EPR pair with some measure of distance. Okay, got it.
That's right. So maybe I could say another word or two about the distance metric. So there's one question you might ask, which is there's this basis kind of question or reference frame question you might ask is, how do I know it's the EPR pair and not maybe 0, 1 plus 1, 0 or something else like that? And actually the answer is you don't know. Actually each prover could locally, do any change of basis they want, and you'd never be the wiser. So what you can say is up to these sort of local isometries, then you know that the state is this close to the EPR state.
Got it.
In the 2 norm of vectors.
Good. Yeah. Okay, thank you very much. That was helpful. Okay, so I don't see any other questions, so let's move to part 2. Thank you, Anand.
Sure. Okay, so in part 2, I'm now going to show you how you use these tests and some other ideas to design these computational protocols. So, okay, remember that we somehow needed to have a protocol that used a lot of entanglement in a specific way, and that's what we have now. So the protocols I'm going to show you are, well, sort of, I guess the history of how we came up with this is that there was an idea sort of called compression that I'll get into over the next few slides. And in this paper with John Wright, the one that Yael mentioned, we were able to use this idea to show that at least you can go beyond NX. So you can actually show that MIP star contains sort of non-deterministic doubly exponential time. So like one exponential factor bigger than the classical thing. And then in the work with Zhengfeng and Thomas and Henry and John, we were able to really push this idea all the way and get up to RE. So I'll first explain how it works for the NEX setting because it's simpler, and then this sort of comes out of sort of a recursive application of this idea. So, but yeah, so the main technique is something that I'm going to describe called compression, and this is actually sort of a theme that's showed up a lot in MIP star research, I'd say, over the last few years, but but in sort of different ways. So the way we actually end up doing compression is a little different from these previous works, but they sort of had like the qualitatively notions of this idea. So yeah, so I guess I'll say what compression is and then explain how we do it. Okay, so compression, it's really just the idea of taking a protocol and producing a new protocol that solves the same problem, but has a verifier that does less work. That's really all that I mean by compression. And so the way that this proof that say MIP star contains any exp is going to work is the following. So I can start from what I know classically, that there's an MIP protocol for NEXP, right, where the verifier takes polynomial time. So the first thing I can do with that is just I can scale up everything by an exponential factor, right? So I could get a protocol for any exp, this doubly exponential class, where the verifier now takes exponential time. So if I've taken whatever there was an n, I'd replace it with a 2 to the n. And then the next step in the proof will be, take this protocol and apply this compression transformation to it, and you'll get a new protocol that solves the same decision problem, but where the new verifier takes polynomial time instead of exponential time. So this compression thing is sort of a way of taking work that the verifier does and offloading it to the prover, so that the verifier now has to do less work. Okay, so that's the basic idea. And then I do want to emphasize that, so this is sort of the step here that's sort of classically impossible. So like actually, because you can show that classically if a verifier only takes polynomial time, then the class of languages you can verify is at most NX, right? So this sort of step cannot be done classically. Okay, so how does the compression work? Well, it's sort of what I said, that you want to take work that the verifier was doing and offload it to the provers. So how do you do that, or what work exactly are we talking about? Well, really, I think the interesting point here is that the verifier does a bunch of things in these protocols, right? It generates random questions and it verifies the answers that the prover sends back. But actually the bottleneck step, like the hardest task that the verifier has to do is to generate these random questions. So, in this protocol that I showed after you scale up, the prover, the verifier has to generate exponentially long random questions and send them to the provers, right? So this is the work that's actually the hardest to delegate to the provers themselves. And if you think about it, just sort of classically, it's impossible to delegate this, because classically there's no way you can force two provers to randomly sample, sort of anything, from some distribution that you control, right? Because they could always, there's no way to force two provers in this MIP setting to even use randomness at all, right? Let alone to use randomness from a particular distribution. So this is where the test for EPR pairs and from quantum entanglement is going to come in. So the idea is that we're going to ask the provers to do this work for us, to generate these random questions by first preparing an entangled state, that's 2 to the n copies of the EPR state, and then measuring it, and then the measurement outcomes will be true randomness, because of the way quantum mechanics works. And then we'll use this, test of EPR pairs to certify that they're actually, doing what we said they should do. So just like sort of as a schematic, I mean, really the way our protocol will look is that the verifier, this polynomial size verifier will send some questions to the provers that will basically ask them to prepare these, this exponentially large entangled state and then measure it in a certain way. And then when they measure it, their measurement outcomes will now be exponentially long classical strings. And they'll interpret those as being the questions that they would have received from an exponentially larger verifier. So this step of preparing the entangled state and then measuring it is simulating a much larger verifier, but it's all happening on the prover's side. But the way we know that it's being done honestly is because we have this protocol that can certify that you really have this quantum state and you're applying certain measurements to it. So that's really the main idea that's going on with compression. And then one other point that I want to make that I think is kind of neat is that remember that in MIP and MIP star, we always have this issue of the fact that the provers cannot communicate, right? That Alice should not be able to communicate to Bob and so on. Now, one thing you might always worry about in these things is that Alice, and Bob are generating these surrogates for random questions in the verifier by measuring this entangled state. And maybe that works. And maybe Alice can get a random question X that's distributed correctly. But we also need to ensure that Alice does not learn anything about Bob's random question, right? Because you want to simulate this setting where the verifier generated these questions and sent them separately. So it turns out that property also can be ensured using quantum mechanics. And really the intuition there is you use something that's basically the Heisenberg uncertainty principle. The fact that if you measure one property of a quantum system, you prevent yourself from measuring some other properties to achieve this kind of isolation. So Alice is going to do a certain measurement. She'll learn this question X, but Bob will do the sort of complementary measurement, a measurement that cannot be simultaneously performed with Alice's measurement. And so the rules of quantum mechanics will prevent Alice from learning anything about Bob's outcome and vice versa. So I think that's a very nice property of quantum mechanics. I mean, this is a theme that's been used, like this goes back to like the BB84 protocol, where you have like different measurement bases, and those prevent you from, if you measure something on the X basis, you can't learn about what happens on the Z basis. And it's just like a classic idea in quantum mechanics, but it's a very powerful one. And that's really what's going on here. So, okay, so that was how this compression works. And so if you do this, I mean, this is basically a schematic of how this protocol for NEX works, right? It's that you start with the NX protocol, scale it up by an exponential factor, and then delegate all the hard work to the provers. So how would you go even further? How do you get up to RE? Well, essentially, you want to take this idea of compression and keep going. Instead of just compressing once, you want to compress over and over again. And that was really the main, I'd say like the main technical challenge in the new paper is designing a compression scheme that can actually be applied iteratively. So the compression scheme that was in the paper with John, that one could only work once. After you apply it once, it sort of stopped. But really what you want is a compression scheme that takes in any protocol for some language and spits out a new protocol that does an exponentially bigger class. That's indeed what we were able to do. So okay, if you have this, you could imagine iterating it any constant number of times, and you could get any tower of exponentials you want, like non-deterministic doubly exponential time, triply exponential time, whatever. How do you actually get up to RE though? Like how do you design a protocol for the halting problem? So this is for this we actually need to use sort of like a clever trick. Some tricks that really go back to computability theory. And I want to say this is also, an idea that sort of showed up in this paper by Fitzsimmons, G, Vidic, and Yuan in 2018. So they sort of thought about these things and in the hypothetical setting where you have a compression theorem, that, there was no compression theorem sort of known at the time, but many of these ideas sort of were first explored there. So really the way the protocol is going to work is the following. So it's going to be a protocol for the halting problem, and it will look like this. So for the halting problem, the input I'm given is some Turing machine, right? I want to know whether this Turing machine halts or not. And so the verifier for this protocol is going to get this Turing machine, and there's also some parameter, n, and I guess like n is like related maybe to the description length of the Turing machine or something, but you could just think of it as a parameter. So what it will do is the following. So the first thing it'll check is that if the Turing machine halts in n steps, that's something you can check by just running it for n steps and seeing what happens, then the verifier will accept. It doesn't need to talk to the provers at all, it'll just accept. If it doesn't halt, then it will ask the provers to run a compressed version of itself. So it'll ask the provers to run the same verifier, but sort of compressed, so it'll effectively run the verifier on parameter 2 to the n. And because of this compression theorem, you can actually ask the provers to do this for you. And you might worry about this idea of referring this weird self-reference here, where like a verifier is asking the provers to run itself. That's actually possible thanks to a fixed point theorem from like computability theory called the clean recursion theorem. So you really can find, like, the thing you find ultimately is a fixed point of this compression map, like a protocol that's equal to its own compression. Okay, so that's the protocol, and it seemed kind of weird, but here's why it actually works out. So if the Turing machine you're given eventually halts, then at some level, some number of levels of steps of compression, you'll eventually terminate, because what you'll do is, maybe it won't halt in n steps, but then the verifier will ask the provers to simulate, the verifier for 2 to the n steps, and then 2 to the 2 to the n steps, and eventually you'll reach some point where, the number of steps here is bigger than the number of steps it takes for the Turing machine to halt, right? And then it will halt, and then the provers will certify that this is the case. Otherwise, if the Turing machine never halts, then eventually this self-compression procedure is going to run out of steam. So the provers are going to try to do it, and they'll discover that they don't have enough entanglement left to do another level of compression. And the reason that's the case is sort of like the provers have to decide on some, even when we talk about the provers having a large amount of entanglement, they have to decide on some fixed entangled state in advance, before they start the interaction. And so eventually they're going to run out of entanglement if the Turing machine never halts. So in a nutshell, that's sort of how the protocol for the halting problem works. It uses this compression to make the provers do this enormous amount of work. Yeah. Okay. So maybe that's this is maybe a good point to pause for questions, because I do think this protocol is kind of counterintuitive, but.
Yeah, that's great. I think it is a great point to ask for a question. So let me just read. I just saw a question, so let me just read it. Or Jeremiah, do you want to ask it live? If you raise your hand, you can just speak, or I can read it. Let's see if there's a. Okay. Yes, Jeremiah, you're on.
All right, let me unmute. Can everyone hear?
Yeah. Yeah.
Okay. Yeah, so this is really exciting work. So I was curious how tight the characterization of MIP star becomes if we assume there's an upper bound, let's say Q, on the number of entangled qubits that the MIP star provers actually have.
Yeah, that's a great question. So I think you can so you can always show an upper bound of like n time of 2 to the q. And I think with this compression technique, you can get a matching lower bound, or a nearly matching lower bound. We haven't really worked it out yet, but it seems like it's possible to me. At least for like any elementary function Q, maybe. I don't know. Yeah, if Q is some weird function, I'm not quite sure.
Thank you. Actually, I have a question. I feel like you're a magician and you fooled us, because how can that be? I mean, okay, you're gonna, each recursion should take some time. Now you can run the, or you have some number of qubits that you decided. And so let's say with this amount of qubits, or you decided to recurse it. So, you know, you'll check if it's 2 to the 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 n. But guess what? It's one more level. So how do you, you see what I mean? So what if the Turing machine actually halts, but the tower is quite big? And the two provers, they had kind of the amount, they don't know how high the tower is.
Okay. So this is actually kind of a subtle point. So it's related to this thing, you know, like in the MIP setting in general, like the provers do know the instance, right, when they prepare their strategy. So they do need to know, you know, how long the Turing machine will take to halt. You know, just like, you know, like in the MIP protocol for NX, like they do need to know the coloring for the exponentially big graph, right, when they prepare their strategy in advance.
Okay, so they actually
can compute it for themselves, like online. You know, I guess the difference with the coloring is that.
But doesn't the run? But the point is that the runtime of the prover should not depend on the length of the tower, because what if the tower is more than polynomial? In other words, here's my question: does the runtime of the prover depend on the height of this tower?
Yes. So yeah, that's right. So the prover will. That's right. So the prover, the operations the prover have to do will have like some complexity that depend on the height of this tower. So maybe like maybe a less magical way to view this is that, say the prover has already had a transcript of like, you know, this Turing machine, you know, somehow they obtained it. Then what this says is that the provers can certify to the verifier that they have a correct transcript. And the verifier will just have to do work that doesn't scale with the size of the transcript. It only has to scale with the size of the description length of the Turing machine.
Yes.
But indeed, the provers will have to do work that you know is going to scale with like the amount of time the Turing machine takes.
Yeah, I think the fact that the verifier's runtime doesn't scale, it's really magical, because there's no way this will happen in the classical world.
Yeah.
You know, because it means that somehow he doesn't check something. It seems like purely quantum-y, the fact. Sorry, Adam?
Agreed. I had a question, but I don't want to take more. I mean, yeah, but yeah, I'll let you.
No, I'm done. Go ahead.
Okay.
Yeah.
So my question, and maybe you answered it, and I just didn't quite catch it, is that, so the provers, your soundness argument, was I correct in understanding that it assumes the prover's state is finite? Like it could be arbitrarily large, but it's an upper bound, and you know there is some finite number of qubits that they share. You know, whatever, 10 to the 300, or the number of particles in the universe, or whatever it is, right? That's
right. Yeah, that's a very good point. That's actually going to show up in the connection to this Kahn embedding problem that I'll talk about in a couple of slides. Yes, that is a crucial assumption that you have to make.
Like, is it meaningful to talk about provers who share infinite entanglement? You know, infinite entangled sets. You know.
Yeah. Yes. So this is meaningful. I will get to that when I get to that slide. So maybe I'll say more about it then. Yeah. That's a great question. Yeah. Thanks.
Yeah, and there's one last question. Evgeny, can you raise your hand so I can unmute you? Evgeny had a good question. And especially if there you go. Hold on. Yeah, Evgeny, can you ask your question?
Yeah, so it's related. I think that's exactly what Yael asked. It's just, I mean, this recursive idea, the verifier is polynomial time. So, and there is some error. It could be tiny, but somehow in fixed polynomial time, maybe, I don't know, the error, maybe it's 2 to the minus n or 2 to the minus poly n. So if the number of iterations could be more than inverse of this error, eventually it seems like the errors have to add up. How can you keep errors from not accumulating in fixed polynomial time?
Right. So yeah, this is also very counterintuitive. And I guess like really one step that I did not show you. So I talked all about like, you know, how you'd get the verifier, how to get the provers to sample these questions for you, you know, these large questions for you. There's also this question of how does the verifier verify the answers that the provers generate, right? The provers have to generate some very large answers. And really what happens is you have to use sort of layers of, you use PCP composition to this. Like, you know, the provers have to certify to you that they're doing these complicated things, and they have to certify this to you, efficiently. So you execute some PCP with them. And there's actually sort of like layers of this. So like really this recursive protocol is sort of like, somehow there's like, a layer of like delegating this verifier to the provers, and then, you then layer on top of it a PCP, and then you also have like a parallel repetition layer that boosts the errors. And so, okay, I guess I can't give like an entirely satisfying answer to it, but like, maybe you can think about it as like, there's like some very, there's like error correction going on at every stage of this compression, like there's like another layer of like, a PCP being put in, which does some sort of error correction. And so if the provers try to deviate a little bit at some level, it'll be caught by one of these error correction steps.
But I guess syntactically, just so that I can visualize, does the verifier do basically only one verification, or really the verifier does like a tower of verifications? Or at the end you're saying the provers do all the verifications, so verifier does only one step? I guess maybe that's the explanation which looks semi-satisfying to me.
Yeah, so the verifier only does, that's right, the verifier only does like the outermost level of verification. So the verifier verifies, so if I have, say, 2 steps of compression, the verifier will only do, it'll get some proof from the provers that they verified sort of the larger inner step, if that makes any sense, right?
Right. Yeah, it does.
Yeah.
Thank you.
Okay, I think we're good to continue for now.
Okay, so we're pretty close to the end. So I guess the last things I want to say is, okay, first, if in case you got lost or you just want to know like what can you take away from this in terms of like qualitative insights, I think we've sort of covered this a little bit in the questions, but okay, where is the magic actually happening in all of this? I think the main takeaway to my mind is that somehow quantum, like quantum mechanics somehow gives you this enormous amount of control over provers that you don't have in sort of other models. Like it's this phenomenon of rigidity or self-testing, whatever you want to call it, of quantum correlations that's being used here. And that's sort of like the difference between both, the classical world and also like the no signaling world that people have brought up. Like those things don't exist in either of those worlds. And so that's sort of why, you can do these kind of crazy things in the quantum setting that you can't do in other settings. And the other point I want to make is sort of like, even though it's like, it seems like, sort of like crazy quantum, techniques, like a lot of these ideas are sort of very old, and hallowed classical ideas. Like they just happen to have go a lot further in the quantum setting. Like, in this protocol, like, a lot of the ideas we use are really just like, things like PCP composition. Like, if you layer like multiple proof protocols with each other, you can reduce the complexity of the answers that the provers need to provide. Or like, this idea of delegating the work of, sampling randomness. I mean, it's kind of in some ways similar to things that show up in cryptography, like this Fiat-Shamir transformation. I'm not at all a crypto expert. So, but my, I feel like, these things are kind of, similar, although that's not like an information theoretic thing, whereas this is. But yeah, I think there's like the takeaway is that, there's a lot of juice left in, these old ideas. Okay, so that was that slide. So now I will transition at the very end to just saying a bit about these implications for physics and math, and then I'll have a few open questions. So okay, so what are the implications for physics and math? They're both sort of very closely related to each other, and I think the best way to explain them is in the framework of something called Searlson's problem. So this is really quite related to this question that I think Adam asked about infinite amounts of entanglement and what that means. So actually it turns out that there's 2 sort of definitions you could write down, if you're just writing down axioms for quantum mechanics of what sort of entanglement or like separated systems mean. And these 2 definitions are different when it comes to the question of infinite dimensional systems or infinite numbers of qubits. So the first definition is something called the tensor product model. And it's really what I've been implicitly assuming in this talk. And in the tensor product model, it's, mathematically, it just says that Alice and Bob, their joint state space is just the tensor product of their 2 individual state spaces. And what that means in practice is that anything that they can do, you can model it as Alice and Bob have, an arbitrarily large finite number of qubits, or you can sort of take limits of this. Anything that they can do in this tensor product model can be approximated arbitrarily well by something that can be done with a finite number of qubits. So that's the tensor product model, and that was really essential. And even this upper bound that MIP stars contained in RE. How do you make this enumeration over all possible strategies work? Well, you have to know that you can restrict to an arbitrarily large but finite number of qubits. So that's the tensor product model. The other model is something called the commuting operator model. And now this one is sort of the one that allows what you might say are truly infinite things. So in the commuting operator model, it's just mathematically, you don't build up Alice and Bob's joint state space out of two separate things. You just say there's one joint state space, and sort of all of the operations that Alice does have to commute with all the operations that Bob does. In this setting, you could have, truly infinite dimensional quantum states that aren't, describable as any number of qubits. And actually, there is an upper bound on, if you look at the version of MIP star in this class, in this world, the commuting operator world, you can show a complexity upper bound on it as well. It's kind of not as intuitive as the MIP star contained in RE upper bound. It comes from semi-definite programming and thinking about some sort of dual objects to these strategies. But you can actually show that in this world, the analog of MIP star is contained in co-RE, the complement of RE. So this is the class for which the non-halting problem is the complete problem. And by the way, just a little fun thing here. So this MIP co, both of these equations, the co stands for different things. So here, CO is for complement. Here, CO is for commuting operator. So it's really totally a coincidence that it's on both sides. But I think a very funny coincidence. And actually understanding the power of this class is an interesting open problem. Okay, but what's Cyrilson's problem? Cyrilson's problem is just, are these two definitions of entanglement equivalent, or is there some experiment you could do that could conceivably tell them apart? So that's a fundamental physics question. So it's saying, is there something that's truly infinite dimensional, or can everything be approximated with finite dimensional things? And the connection to math is that there's a long-standing conjecture in operator algebras called the Kahn embedding conjecture, or I should actually say the Kahn embedding problem. that it's a problem, and people didn't necessarily conjecture that the answer was yes, but sort of if the answer is yes, then by a number of known sort of connections, that would imply that the answer to Cyrilson's problem is also yes. It implied that the tensor product model is equivalent to the commuting operator model. And then, by following these, these complexity theoretic arrows here, sort of if that were true, if tensor product and commuting operator were the same, then these two complexity classes, MIP star and MIP co, would also have to be the same. And that would mean that they'd have to lie in the intersection of RE with co-RE. So if you remember your computability theory, that's just the set of decidable languages, which is called R. And it's known to be not equal to either RE or co-RE. There are undecidable languages in both these classes, so their intersection is not equal to them. So what did we show? I mean, we show that MIP star is equal to RE. So that implies that it's not contained in the intersection of these two things, and therefore MIP star and MIP commuting operator are not the same. And so you can just follow all the arrows backwards, and you get that this old conjecture in operator algebras is actually false. So that's the consequence. And then maybe the way I'd interpret this is, it does seem a little bit magical what's going on here. And I definitely don't have a nice explanation for this top arrow here. But here I'd say that what's going on is this MIP star protocol for the halting problem is itself kind of the experiment that distinguishes the two worlds. So, and how does it do that? Well, it's a sound protocol only in the tensor product world, where you can assume that everything is approximable by finite numbers of qubits, but it's not sound anymore in the commuting operator world. So that's the test that you could do to distinguish between them. Yeah.
Anand, let's wrap up because I want to leave time for one great question that's waiting.
Sure. Okay. Well, that's good. So okay, this is my last slide. So okay, I just want to say that there's a bunch of cool open questions. Can we extract insights from this for quantum cryptography or quantum computing, but also maybe math and physics and so on. But yeah, I guess I'll conclude here. Thanks.
Thank you so much. Talk was great, really, really great talk. And let me end a great talk with a great question by Rohit, who asked the following: is there an analog of compression with a single prover in the single prover setting, or is this kind of tied to the multiple prover setting?
Yeah, okay, so this is a very good question. I think we don't know yet. The thing you need first is an analog of this like rigidity thing, these tests for EPR pairs in the single prover setting. And that is a topic of active research right now. So in this single prover setting, you need some sort of cryptographic assumption. Like you can't do things, information theoretically secure. But I think it is known now that, if you assume something like, some like one-way functions exist and are hard, maybe you need these like trapdoor, like claw-free one-way functions, then I think you can do at least like the CHSH game. Like there's some recent work on this. And okay, it remains to scale it up to, larger entangled states. And yeah, we don't know if that'll work, but it seems plausible that such a thing might exist.
Got it. Okay, thank you so much. Thanks again. The talk was amazing. You said that you're not a crypto expert, but don't worry, you'll come to town. We'll all be sure to convert you to one. And okay, so this was great. I guess we're at the end of the conference, and I'll let Daniel end with some concluding remark. But let me just say thank you to everyone. This was great. I learned a ton. The talks were just phenomenal, and I'm really looking forward for next year. Okay, Daniel. Thanks.
Great. Yeah, thanks. So I don't have actually much more to say beyond that, but just wanted to thank everyone again. This was really, really wonderful. So surpassed my expectations of what I thought this would be like. Not only did everyone show up, was on time, everything like ran smoothly, but the talks were really amazing. People did a great job preparing it. So I thought it was a great precedent or a great bar to set for the first ITC conference. I think, yeah, if we continue on this trajectory, it's going to be a great conference going forward. So, hopefully hopefully next year we'll actually see all of you physically and in some place. And actually, Benny told me to advertise that if you want to organize ITC and be a general chair, we're looking for general chairs. So if you want to volunteer to host ITC for next year, let Benny, who's the head of the steering committee, know. And yeah, so great conference. Looking forward to seeing all of you physically next year at the next ITC.
Great, and let me just end by saying, Daniel, huge thanks for being the PC chair, for getting a great committee, and for bringing this great conference to life. Really, I'm super impressed. It's been just delightful. So huge thank you. Okay, guys, see you next year, hopefully.